Hi folks, Mr. Ackerman here. Thanks for watching. The topic of today's video is electric forces and Coulomb's law. We're going to start looking at one of the other fundamental forces, this one, of course, the electromagnetic force, and specifically we're going to look at how forces are exerted and how to measure the forces exerted between charged objects. And along with that, we're going to learn something called Coulomb's law. So take a moment now to pause the video, have a look at where we are in the unit schedule, as well as what the learning goals and success criteria are, and then rejoin us. Okay, you're back, and here we go. Let's get started with a brief background discussion of the law of electric charges and what we mean by electric charges. Of course, when you think about electric charges, there's any number of things you might think of. You might think about a time when you took laundry out of the dryer and found that a lot of the different pieces of clothing were sticking together, and as you pulled them apart you heard a crackling sound. Maybe you took a sweater off and it rubbed against your hair and you found that your hair was standing on end when you took it off. Maybe as a kid you rubbed a balloon in your hair and you were amazed by how it stuck against the wall. Maybe you have a more sophisticated view of electric charges and you think of atoms and the protons and electrons that are in those atoms. Whatever the case may be, electric charges obey a certain rule. We call it the law of electric charges, and of course many of you are familiar with this. It says that like charges repel one another and opposite charges attract. So I'm going to write here, like charges repel and opposites attract. Now you have to be careful. If we're talking about individual point charges, such as maybe two protons, which I'll designate like this, then yeah, they're going to repel one another. If we're talking about two electrons, then they're going to repel one another. If we are talking about something charged, like a balloon that you rubbed in your hair, and not much of an artist here, I'll do my best with the balloon. This might be a balloon that is charged, maybe it's charged negatively, perhaps, which is actually what would happen if you charged it by rubbing it in your hair. If you brought that near the wall of your house, it's not a very straight line, let's try that again. If you brought that near the wall of a wall in your house, you would actually find that these attracted one another even though the wall is neutral. And so what is strange here is that this sort of attraction might make you wonder, well, what's up with this part of the law of electric charges which says opposites attract? I mean, I know what opposites would be. That would be like a proton and an electron. They would attract one another, of course, but so would that balloon against a neutral or no net charge wall that I experienced when I was a kid. What's going on there? Well, the thing that's happening here, and if you want to read about this some more, you have to look back to the previous section in the textbook, section 7.1, that textbook being Physics 12 by Nelson. What's going on here is there is a lot of charge on this balloon, and it is affecting the many charges that are in the wall, and it's actually leading to a separation of charge, which causes part of the wall to become positively charged, part to become negative. In fact, what ends up happening here is part of the wall becomes a bit negative, part of it becomes a bit positive, all due to the influence of the negative charge on the balloon. And then what happens is it's this negative charge accumulated on the balloon and the positive charge that was due to the charge separation in the wall. This is actually what is attracting. So just want you to distinguish between whether we're talking about individual point charges like protons and electrons, or are we talking about extended objects which have a larger charge distribution. Just keep that in the back of your mind in this unit because it will be important. Of course, if you have, for example, neutrons, like a neutron here which has no charge and an electron, there will be nothing. There will be no electrical attraction or repulsion. And if you have a neutron and a proton, there will also be no electrical interaction there. And I just again wanted to distinguish between this situation, which are point charges, and this situation, which started with a neutral wall, yet resulted in attraction. There's something different going on here. To find out what, do a quick review of section 7.1, which talks about induced charge separation, which is actually what's happening here. But anyway, getting back to what we're going to be discussing, since these charges are attracting and repelling, it's natural to want to talk about the forces that are involved. And forces in this situation are described by something called Coulomb's law. So what is Coulomb's law? Well, it's just a formula for calculating the number of newtons of force exerted when charges come near one another. I'm going to write out the formula for you, and as I write it, I want you to ask yourself whether you've seen something similar to this before. The answer is going to be yes. F electric is equal to K times the letter Q, big Q, times the letter little q, divided by r squared. This is Coulomb's law, where Q and this Q are equal to the quantity, that's why we're using the letter Q, of electric charge. Now, if you recall from grade 9 or grade 11, electric charge is measured in coulombs. Letter for that is C. So, for example, you might see something like Q equals 0.2 coulombs. That's how we would write a quantity of electric charge. R is equal to the distance separating Q and little q, big Q and little q, and that of course is in meters. And K is a constant which is equal to 9 times 10 to the 9. And what are the units here? Well, we know we want to get newtons for force, so we've got to have newtons in here. We've got a denominator of meters squared, so we've got to have meters squared in the numerator to cancel that out, and we're going to have coulombs times coulombs in the numerator. That's coulomb squared, which here we'll need in the denominator to cancel that. So here is your value for K. All right? And so that's it. That I could actually stop the lecture or the video here, and I'm sure some of you wish I would, because with this you can actually figure out a lot of stuff in this unit, but there are a lot of details that we do have to talk about, so unfortunately for you I'm going to continue here. However, this formula, if you sub in the numbers, you should get the number of newtons of force between two objects. Now, if they are protons or electrons, for example, then these are very, very tiny objects. The distance between their centers will be equal to the distance between them. They don't occupy much space at all. However, if I'm talking about a balloon and a wall, what do I pick as the distance here? Here things get a little bit trickier because the wall may not have an obvious center, neither would the balloon. In this case, what you'd actually have to do is realize that balloons are made of many, many charged particles, lots of atoms with protons and electrons. Same for the wall. And you actually have to add up all of the force vectors from those charged particles in order to figure out the net force on here. And you're going to see me doing something along those lines a little bit later in the video. But for now, this is Coulomb's law, this is the formula, and now we're going to apply it. Actually, before I do that, let me just point out one thing. I did tell you before I wrote this down that you've seen something like it before, and I should actually follow up on that. What have you seen that looks like this? Remember this not too long ago? Newton's universal law of gravitation. Surprisingly, these two have the exact same mathematical form. And so one of the neat things is that if you want, in this unit, you can do the following. You can think of masses as behaving the way charges do. Distance, of course, is still distance. Think of G like K, and of course force is still force. So a lot of the math that we're going to do in this section here is going to be similar to the math here, and that's going to make it easier to go through this particular chapter. All right, so let's begin that journey and see what it looks like. Let's do a simple example using Coulomb's law. I'd like you to imagine an atom, maybe a hydrogen atom. Think back to what is a hydrogen atom. Well, a simple hydrogen atom is a proton with an electron orbiting. And that's all it is. This is neutral hydrogen. Now, how far apart are these? Well, if you go and look it up, you'll get sometimes different answers. But as a rough approximation, a number that I remember from university is 0.5 of this strange symbol, an A with a 0 on top of it. What is an A with a 0 on top of it? It's an old unit that not many people use anymore. It's called an angstrom. It's used a lot in older astronomy books. And since I studied astronomy, I remember this. What is an angstrom? An angstrom is 1/10 of a nanometer. What's a nanometer? You got to know your metric prefixes. A nanometer is 1 × 10⁻⁹ meters. So here's your nanometer. Here's the 1/10, and that is an angstrom. And the distance between the proton and the electron in this model of the atom is half of that. So actually, the R value separating these two is 0.5 times 0.1 times 10⁻⁹ meters. And surely we can move that decimal place. We can move this one 1, move that one 2. It's going to give us 5 by 10⁻⁻11 meters. Okay, so there's our distance. And now, what is the charge on these two? Because if you remember back in the previous screen, we need to know not just the R value, but the charges. Well, I hope you remember from chemistry class or some other class that the proton and electron have the same charge. So we could put Q for the proton, let's say, and we could have little q for the electron. They are the same, and if you look them up, you'll notice that one of them is, of course, positive and one of them is negative. The value to two significant digits is 1.6 times 10⁻⁹ coulombs. That's right, they're not 1 coulomb. They might be one particle, but they are a very tiny number of coulombs of charge. One of them is positive, one of them is negative. Now, when you're writing out the force formula, K big Q little q over distance squared, students always ask me, do I have to sub in the positive and the negative? Well, you can if you want, but it's not necessary, and I'll tell you why. This formula is really telling you the magnitude of the force. It's your job to figure out whether we're going to have attraction or repulsion here and what direction that's going to represent. So for example, you know that opposite charges are going to attract. So I could write here that the proton feels an attraction to the electron, and at the same time the electron feels an attraction to the proton. So by putting in positives and negatives in this formula, you might end up confusing yourself, because which of these two forces will we be talking about? The force of the electron pulling the proton to the right, or the proton pulling the electron to the left? If I tell you to put in positives and negatives here, you're going to get confused. So I usually tell my students, think of this as magnitude only, and deal with the direction by remembering the law of electric charges. Like charges repel, opposites attract. If you can keep that in the back of your mind, you'll always be fine, and you don't have to sub in these positives and negatives. Anyway, let's see what we get here. 9 times 10 to the 9 for K. Not worrying about negatives, 1.6 by 10 to the negative 19, and another 1.6 by 10 to the negative 19. We're going to divide that by a very small distance of 5 times 10 to the negative 11, and don't forget to square that. And now I'm going to take a moment to pause the video and do a calculation. I encourage you to do the same. Let's see what we get here. Okay folks, so what did I get on my calculator and what did you get? Hopefully we both got the same thing. I got 9.216 times 10 to the negative 8 newtons of force, which is a very, very tiny force indeed. Although keep in mind that these objects are very, very tiny. So while they're experiencing tiny forces, since they themselves are very tiny, that may lead to very large accelerations in the classical model of physics, where we think of forces as causing acceleration. Of course, if you're a student of quantum physics and you understand a little bit about atoms, you'll realize that atoms don't quite work that way. So when I talk about force and acceleration within an atom, you can't quite think of it that way. You have to study quantum physics to see what's really going on there. But anyway, the point hopefully you understand. Okay, so now what we're going to do, this electric force to a gravitational force, just to give you an idea of how the two compare, because we have been talking about fundamental forces. What I'd like you to do is go back to the H atom. This is a little exercise for you to do on your own. And using the same separation distance and using the information you know about protons and electrons, which may or may not be much, I want you to calculate the gravitational force that is attracting the two of them. So just for fun, go back to this formula, and I'd like you to look up the mass for a proton, and I'd like you to look up little m, the mass for an electron. Of course, the R value is still the same as before. There you go, a little bit of time saved. And I'd like you to calculate the gravitational force attracting these two. And then I'd like you to compare them. When we do a comparison in math, we often divide. So we divide one value over the other to get a ratio. So this is what you're going to do on your own. You're going to take Fe, which we already have, it was calculated up here, and divide that by whatever you get for this. Of course, you're going to have to do some looking up. You've got to find the mass of a proton and electron. That's your job. And what number do you think you're going to get? Which force do you think is stronger? Will this value be equal to 1, same force? Will it be greater than 1, electricity stronger? Less than 1, gravity stronger? Or what? Well, when you do this, I will tell you one thing. You should get a huge number, like 10 to the lots. Think of it that way. You're going to find out that the electric force is much, much stronger than the gravitational force, which is what scientists have found. The gravitational force is actually the weakest of the four fundamental forces. The electrical force is next up in second place, or in third place. Then the two nuclear forces come. All right? So check that out on your own. Maybe in class we can discuss the actual number. But if you're not getting 10 to a very big number, I think it's around 35 or 6 or 7 or 8, then you'll know that you've made a mistake. And this, by the way, is the fact of the video. The fact of the video is going to be the ratio of these two forces. So make sure that you can do that when you come to class. And I guess you might need to do some memorization of charges, distances within an atom, and masses. All right? Very good. Moving on. Let's take a look now at a slightly more challenging example involving electric forces. This one here is a two-dimensional example involving forces. So I'm wondering how you would deal with this. I'm going to set up a problem for you. I'm not going to solve it. I'm going to leave it for you. But the reason I know you're going to be able to do it is because it's going to build on old ideas which should be familiar. So here's what to imagine. Imagine a square. So since I'm telling you this is a square, that means the side lengths are equal. And let's suppose that those side lengths are, just to keep things really simple, 1 meter. Okay? At each corner of the square is a point charge. And let's give these names like QA, QB, QC, and QD. Now let's give them values. Let's suppose that this one had a charge of 1 microcoulomb, positive. And let's suppose that this one had a charge of -1 microcoulomb. Suppose this one also has a charge of -1 microcoulomb, but suppose this one has a charge of +2 microcoulombs. Now, a few things. First of all, what is a microcoulomb? Well, again, you guys are grade 12, you're university bound. That means you know your metric prefixes. I shouldn't have to tell you this, but just in case, mu, which is micro, is 10 to the negative 6. Your university professor will definitely not give this to you on a test. So consider yourselves lucky that you're spending time with me for one more year and then you're on your own. So make sure you learn those. The question is as follows. What is the net force? I guess we should specify the net electric force on C due to A, B, and D. So think about that for a minute. Pause the video if you have to. What is the net electric force on charge C due to A, B, and D? Okay, and you're back. You've had some time to think about that. What do we mean by this? Well, let's analyze the situation. Remember what we know about electric charges. We know the law of electric charges. Like charges repel, opposites attract. We also know how to deal with forces. We've been doing it for a while in this course now. So let's see if we can't figure out what's going to happen to C as a result of A. A is positive, and C is positive, so they're going to repel one another. They repel along the line that joins them, and so I could draw a vector pointing this way, and I might give it a symbol F, A on C, or maybe FAC, just to keep things simple. For that matter, B and C, they are oppositely charged. This one's negative and that's positive, so C will be attracted to A. So I should draw a vector like this. But how long should this vector be? Should it be longer than the vector I just drew? Shorter? I'm going to make that a question mark for a second. Let's analyze. This was a 1 Coulomb charge, 1 microcoulomb, fighting a 2 micro, or repelling a 2 microcoulomb charge. This is just a 1 microcoulomb charge again, attracting a 2 microcoulomb charge. But if you look at the geometry of the square, this distance is closer. So I should actually draw this line longer than that one. So I'm going to undo what I did here because I didn't draw a really accurate representation. I should have drawn a longer line to try to be as representative of the real situation as possible. We're going to call this the force of B on C. Now here's something that every physics student loves. It's when you can use the symmetry of a problem. The symmetrical nature of this problem means that this vector will actually be the same length, although a different direction, as this one. This is FD on C. Charges are the same, the distances are the same, just the direction's different. So look what I've got here. I've got 3 forces acting, and I can calculate these, can't I? This one's going to be K, QA, QC, over the distance, RAC. Don't forget to square. What is that distance? Well, it's this distance here. How are you going to find that? I think you know what to do. You're going to use Pythagorean theorem. We've got a square, a right angle, side lengths of 1, and here is your hypotenuse, right? What do we do for B on C? Same sort of idea. QB, QC over the 1 meter distance squared. And similarly, well, I'm going to leave it to you. You know what to do with this one, right? Now, we're in 2 dimensions, so guess what? We've got to use components. Remember those? So here's what I'll do. Let's shrink this down a little bit and move it up to there. How do we do this? We write out our forces. FB on C is something, comma, something, plus FA on C, which is something, comma, something. Add that to FD on C, which is something, comma, something. Need a little bit more space here. that's going to give you F net, which is something, comma, something. Need a little bit more hint? No problem. Try this. Make these your positive y direction. Make this your positive x direction. And now I think things should be starting to come back to you how to do this. Find the net force. Don't forget to find its magnitude and its direction. It's hard to tell from the diagram exactly what's going to happen, but I think if you use symmetry and knowing that these two forces here are longer than that, I think you're going to end up with this one and this one adding together to give you something quite long on that diagonal, and then you're going to subtract a little bit due to this. So you should end up somewhere with maybe a net force, I don't know, something like that perhaps. So check that you get an answer with an F net with an x value that is a bit negative, going this way, and a y value that's a bit positive, going a little bit that way. All right? I don't know the exact number. I haven't worked it out myself. I've left this for you, and we can take it up in class. That way I can save a bit of time on the video. All right? One last one, just to get your head in the game. I think you'll find this one a little bit easier to deal with now that you've seen the previous one. There's a question in your textbook, Physics 12 by Nelson, where you're going to see the following. There is a rope suspended from the ceiling at a certain point, and the rope hangs down like this. They suspend it in the middle, and to the ends of the rope, they attach two objects which are charged up. These could be balloons, they could be a styrofoam ball that's been rubbed in your hair, something like that. And they've charged them up equally so they repel one another. And as a result of repelling, they hang at an angle. Whoops, I just lost my screen. Hold on a sec. Okay, and I'm back. Haven't done that in a while, but every once in a while it happens. So as I said, there are two objects which are equally charged and they hang at an angle. And because they hang at an angle, this angle in here is equal to that angle in there. And you're given, I believe, a length for this side and a length for that side. I think they tell you there's something like a 60 centimeter string, if I recall correctly, and we pinch that off in the middle and let it hang down like that, so each side is like 30 centimeters. Now, what they ask you is, if this is hanging at a certain angle, then can you tell me what is the charge on each object? And they give you the mass of both of those. I think they say they're identical, and that's why they hang at equal angles. So let's think about what forces are acting on here. Let's look at just one of the masses. Can you guess what the forces are? Can you draw a free body diagram? Take a moment to pause the video and do that. All right, and you're back, and let's see what we got. Well, if you wrote down that gravity is acting, then you're definitely correct. There is gravity acting here, and that, of course, would be equal to mg. What other forces are acting? Well, there's a string, and so there's definitely going to be tension in the string, and that, of course, acts along the length of the string. So let's write that in, Ft, like that. And finally, what is it that's pushing these two apart? Well, it is the Coulomb force, the electrical repulsion of like charges. Of course, if they were attracting, we wouldn't have the same kind of situation, but this is Fe. And recall once again, the question tells you that these have a charge, so I could even write the letter Q and Q. I believe they're charged equally in the question that's in your textbook there. So what they ask you to do is something like find the charge that's on them, given that the objects hang in static equilibrium. What are you going to do? Well, can you see how this question is very similar to the previous one? You're going to write out your positive and negative direction. You're going to use components. You're going to add them up. And this time, the net force is going to add to 0. So get yourselves ready to write the following. Fe equals, let's see, this is something in the x direction. That's going to be a k. The two q values, which are the same, so I'm going to square them, divided by the distance between them squared, but nothing in the y direction. And since this is pointing off to the left, and I usually make positive to the right, I have to be careful. I need a negative sign in there. What else is this being added to? This is being added to gravity. Gravity, of course, 0 in the x direction, negative, all of it in the y direction, so you have that. And then finally the tension. This one has x and y components that are non-zero. Looks like I'm going to have to start thinking angles here. So what have we got? If this angle is x here, then that means this angle will be x as well. So what would I have? In the x direction here, I would have a positive ft, that's going to be a sine of x. And in the y direction, I'll have a positive ft cos of x. And supposedly, all of these add to an f net of 0. And so the question basically asks you, if I remember correctly, to solve for the charge q given everything else. Well, you know k, that's not too hard to find. If you know the length of this string, and remember we talked about it up here, I believe they're 30 and 30 like that for a total length of 60, then you can use the angle in here and a little bit of triangle math to figure out the distance. The angle is given. There are two equations, the x equation and the y equation, so you can solve for the tension force and the charge. That's kind of how this one goes. So welcome back to forces in 2 dimensions. This time we're just adding a new kind of force. We've seen how that new kind of force can be used in 2 dimensions. We've seen it used in 1 dimension. We've seen an interesting comparison between 2 fundamental forces, and we've revisited the law of electric charges, as well as a little bit on how multiple charges behave, which you last studied in grade 9. All right, so hope that wasn't too much, but happy studying, and I will see you guys in class. Thanks for watching.